Hey, welcome guys, this is Mr. Sheeline. Today we're going to be going over the 2.2 notes for nuclear decay and also percent error. These are the notes, 2.2 notes for chemistry. If you don't have these, you don't have the physical copy of these, make sure you check on Google Classroom to snag the student version so that you can print them off and then follow along with this video, okay? All right, let's just get right into it. So what is radioactivity? What is radiation? And so simply put, as far as we, for the most part, we've heard of this term before, but to actually give it a definition, it is the spontaneous emission of radiation from the nucleus of an atom. Okay. Now we've heard of radioactivity in different, contexts. So, maybe we know radioactivity from, movies such as the Hulk, or comic books, I guess, from the Hulk, where Bruce Banner was exposed to too much gamma radiation and turned him into a giant green thumb, more or less, and other areas such as, like, if you go back and see a lot of movies, or at least see a lot of content from the 70s, from the 80s even, remember at that time people were still reeling from and still dealing with the Cold War, so there was a lot of movies, there was a lot of media, there was a lot of propaganda that was created, centering around radioactive materials, because there was imminent danger at any given moment of an attack with potentially harmful materials that were radioactive. So we've heard of this word before. We, for the most part, understand that it's something. So the best I can do to remind you is that, radioactivity is nothing more really than just a transfer of energy, okay? It does sound scary, and it is, like, don't get me wrong, it's dangerous for the most part, or at least in the types of radioactivity you hear in the news or you hear in media. But remember, radiation is nothing more than just the radiation, something radiating energy. Because I can tell you the first thing I can think of when I think of radiating, I think of the sun. So which, again, dangerous, yes, because we can't even stand on the surface of the sun, because A, there really is no surface, and B, within a couple million miles from the place, we pretty much just burn up. But anyway, what I'm trying to get at is that it's not a scary term. We should be comfortable with it, and it's something we've seen before. Okay. So tying in with radioactivity, because we're going to be talking about different ways that energy and different ways that energy and other materials are radiating from atoms specifically. We also then have to talk about what's referred to as the strong nuclear force, the SNF. So the strong nuclear force is the attractive force acting between all subatomic particles, so your protons and neutrons, within your nucleus. Okay? The SNF is what holds the nucleus together against the repulsion force created between the protons. So remember, protons are all positive. Okay, the protons are all positive, and as we know, the little bit that we know about electroconductivity and magnetism is that if you try to put a positive end of a magnet with another positive end of a magnet, and you try to put, or even a negative end and a negative end, and you try to push them together, you'll get repulsion force. Okay, and so that's why that's why we're specifically talking about protons, because those positive that positive that positive energy, or positively charged energy, I should say, and protons want to push away from one another. They want to find that opposite. They're trying to attract towards something negative, say an electron. Okay? Well, the strong nuclear force is what keeps that all together, so that they just don't spring out of the atom. Okay. And then, somewhat inversely, we have the weak nuclear force, the WNF. So this is the attractive force acting between particles in the nucleus over extremely short distances. Okay. So to break it down, I guess, into kind of a visual, to understand the difference between the strong nuclear force and the weak nuclear force would be like this. So the strong nuclear force, more or less, because this is not something I test you on. This is just some way, a better, it's some, what I'm going to be testing you on is to know the difference between these two. But to kind of make an image of it, so here's our strong nuclear force. This is what this looks like. So if this is our, if this is the nucleus of our atom, okay, this is the nucleus of whatever atom. The strong nuclear force, okay, is more or less doing this. It's applying a force here that is just keeping everything locked in, keeping everything nice and tight within that little ball we call the nucleus, okay? And it's a tightly packed form of energy that, if broken, will, because it's just so immensely, great of amount of energy, it causes kind of a bad thing, which is an example we're going to be seeing later on in the notes. Whereas the weak nuclear force, so if this is now the nucleus of our atom, so this is the nucleus of our atom, okay, we have, we'll have our protons in here, and then, or I'll put P's on there too, and then we're going to have our neutrons in here, in no particular order. But here are neutrons, okay? The weak nuclear force, and here, let's actually blow this up. So let's say we're grabbing this guy right here. So kind of make a blown up image of that right there. The weak nuclear force is going to be the attractive forces like in here. It's going to be the forces that are found within your nucleus, that are pushing and pulling together the different subatomic particles, kind of keeping them together inside. Okay, so that's more or less visually. This is the difference between the strong nuclear force and the weak nuclear force. This one deals with the strong, or the force packing tightly together the atom, whereas in the weak nuclear force is just the force found within the nucleus of the atom between the different protons and neutrons, more or less. Again, more of a visual than it is, for anything else. Okay. So why is this important to know? Why do we have to know about, the strong nuclear force, the weak nuclear force? Well, it's important to understand that we know that there are forces, like there is something that's holding this together. It's not just some random, oh, this guy just wants, this proton wants to hang out with this neutron, or, oh, they just happen to fall that way. No, there's something that keeps these together. And when these are when this force is disrupted, when you have, say, protons or neutrons leaving, or certain electrons that come in and come in violently, there are things that change in relation to this. Okay, because this is what holds your atom together. And in order to stay stable, your atom has to adjust. Your atom is more or less changed. So what do I mean by that? So let's take a look here. So there's different kinds of radiation that disrupt our strong nuclear force and our weak nuclear force. Now, it's not to say that it completely breaks your strong nuclear force, but it disrupts it a little bit. Let's be frank here. It gives it a little hiccup. Okay. So you have what's called alpha radiation. So alpha radiation is denoted with simply alpha here. That is your alpha signal, alpha Greek letter. Radiation, and this is the radiation consisting of 2 protons and 2 neutrons. Okay. So what does that mean? Well, that means that an atom is going to radiate. An atom is going to lose 2 protons and 2 neutrons. Okay. Now, why would it do that? Well, we don't get into exactly why it does that. But what we do know is that it does, or at least in this class I should say we don't get into that, but what you need to know is that it does happen. Okay, so we know, now that we know it does happen, we understand what's at stake here. Well, let's kind of look at, you know, how we can kind of break this down. So first we have to denote this little thing right here. And excuse my other notes in here, but I'll make a mention of these. Okay, so each of these is how we denote the alpha particle. Okay, so that's all this. That's what these three are. These are our alpha particles. That's what they're referred to as. Okay. So we can denote it like this. And if you notice, it's pretty much just all chemical symbols. But we can denote it like this, where we have alpha, and then we've got a 4 and a 2. Or we can have helium with a 4 and a 2. Or we can have it an ion, a helium ion, where it's helium with 4 and a 2. Now remember, the 4 and the 2, what do those represent? Well, the 4 up top is your mass number, as I've written here, okay, which you should write down too. So your 4 is your mass number, whereas your 2 is your atomic number. We'll get to this in just a bit, but your 2 is atomic number. Okay. Now, if you're wondering, Mr. Sheeline, okay, so it's going to lose this particle. It's going to lose this alpha particle, our atom. Why then are we writing helium? What does helium have to do with anything? Well, I have to ask you then. Well, what has 2 neutrons and 2 protons? An atom of helium. So that's what helium has to do with this, is that these atoms, more or less, are losing a helium atom. Now, that's not to say all of a sudden that, you know, maybe tellurium or arsenic, gallium, whatever atom you choose, has like helium atoms in it. No, that's not exactly what I'm saying here. What I'm saying is, what it's losing is equivalent, is the same thing as a helium atom. Okay, so, and if you're still confused by that, think of it this way. If you lose 2 protons and 2 neutrons, what has 2 neutrons and 2 protons? It's a helium atom. So it's this idea that once we take out 2 protons, specifically when we take out 2 protons, and you got 2 protons and you also have two neutrons as well, you have a helium atom. That's what's happening here. Okay, so that may seem kind of weird. Trust me, like if you still have issues with this, you can come and talk to me. But trust me, like this is, for the most part, this is what's happening. Okay, so now let's get to this indicates reaction. So this is how we would denote. This is how we would write out our reaction. So let's say we started with cesium. We've got cesium 133. Okay, and remember, even on cesium, that 55, that's the atomic number. And the 133 is the mass number. Okay, cesium is going to undergo alpha decay. Okay, so how do we write that? Well, first what we have to do is we have to write our little arrow here, and we should recognize this from either physical science at one point, or we should recognize this from just any other science class. Okay, arrow indicates a reaction. Okay, almost think of it as like an equal sign in math. Okay, kind of. It's not exactly the same thing, but think of it in that kind of way for chemistry. So we have to indicate. We have to have our arrow here indicating a reaction, and the reaction that's happening is that cesium is losing this alpha particle. So in this case, we denote it with the alpha sign. We could have used the helium sign. It doesn't really matter. It's both the same thing. But it loses an alpha particle. We put a plus. Okay, meaning that these two things are separate and distinct. It's not to say that they're going to be added together because they've been separated. Okay, but we put plus, indicating distinction, indicating these two are separate. Then our cesium has now turned into iodine. How do I know it's been turned to iodine? Well, let's compare. So remember, an alpha particle has 2 protons and 2 neutrons. So what's happening here? Well, cesium is losing 2 protons and 2 neutrons. So what happens? Well, what happens is that your atomic number here is going to decrease by 2. Whereas in your mass number, because you're losing 2 protons and 2 neutrons, it'll be subtracting 4 from it. So that's why we see here 133 minus 4 is 129. 55 minus 2 is 53. So when we're doing this ourselves, and we're gonna do one here in just a bit, try it out by ourselves. But when we do this, we're gonna start with this guy. You draw your arrow, then you draw this guy, and then it's gonna be 55 minus 2. Okay, then that will give you 53. And so then what you need to do is you need to grab your periodic table here, and you need to find out who has 53. There, iodine has 53, so that there you should know that, oh, I'm working with iodine now. And then you go back and you just 133 minus 4, 129. And you write it such as that. Okay. All right. So let's try out with bismuth. Okay, let's try this out. So we're given bismuth 209. Okay. So bismuth is going to undergo alpha radiation, alpha decay. So we're going to draw our arrow. After we draw our arrow, we're going to mark our alpha particle here. And then after we mark our alpha particle, we're going to mark plus. Now I want you to pause the video and I want you to figure out, okay, what's this going to be? Okay. Okay, so let's figure this out. So 83 minus 2, that's going to give me 81. 209 minus 4 is going to give me 205. I'm going to look on my periodic table. Oops, wrong one. I'm going to look on my periodic table, and I'm going to see which what element has 83. And it looks like, or sorry, not 80, 81, not 83, 81. And it looks like, so let's see, here's bismuth, here's 81. So it looks like thallium, because I look up here at the atomic number, and I see thallium has an atomic number of 81, and its chemical symbol is TL. And then I have my answer. So let's double check to make sure that's right. Boom. Look at that. Perfect. Okay. So that's what we're doing here. We're showing that these things are losing the particles, these alpha particles. Okay, so let's move on to another kind of radioactive decay. That is beta radiation. So beta radiation, this is consisting of a high-speed electron. So what's happening here? I'm glad you asked. So what's happening here is that this guy right here, so this is how we denote our beta particle, more or less. Our high-energy electron is really what it should be called. So here's our high-energy electron. We denote it with beta, or with an E, and then we have 0. That's still the mass number. But, of course, because electrons have no mass, more or less, or at least it's so incredibly small that it's pretty much negligible, we put a 0, but we still want to put the charge down, which is -1. Okay, and we, again, just like up here with the alpha particles, we can either show it like this or we can show it like this. So what's happening here? Well, what's happening here, real quick, what's happening here is you have an atom here minding its own little business, and you have a high energy, like Super Saiyan electron here just going absolutely nuts. And it's going to slam itself into an atom here. And because this electron is not only just carrying its negative charge with it, it also has quite a decent chunk of energy with it. It's going to destabilize your atom here a little bit. Okay. And what I mean by it's going to destabilize it a little bit, I mean there's a good chunk of energy slamming into it that it has to change in order to compensate for this new amount of energy. So what happens? Well, this is what happens. So in your atom, remember you've got your protons and you've got your neutrons. So here are, I'm going to make these my protons here. Okay. You have your neutrons here. So more or less what happens is that when this guy slams into your atom here, what happens is this, is that you'll have maybe, let's say this guy, This guy is going to say, whoa, we can't handle this amount of energy. Something has to change. I'm going to change myself so that I can compensate here. And then this is what you're left with. This is what happens. What happens is, in super basic terms, super duper basic terms, you have a neutron that turns into a proton. Okay. How does it do this? Why does it do this? Well, we won't get into it terribly, but what I'll say is that just real quick, in protons and neutrons, you have this. So this is, let's say this is a neutron here. You have inside of this what are called quarks, and more or less quarks identify, or at least signify at a given moment whether a proton or whether or not a subatomic particle is a proton or neutron or not. That's as much as I'm going to get into it, because this is even going past what I know about quantum mechanics and quantum physics. But more or less, there are little things in here called quarks that can change a neutron to a proton. And that's what's happening here. So again, what's happening, you have high energy electrons slamming into an atom. An atom, in order to compensate, changes a neutron to a proton. Okay, because if you have too much energy out here in your cloud and there's way too much energy to handle, you have to counteract and balance out. You have to counteract and balance out that negative energy on the outside with positively charged energy on the inside, so you don't have an unstable atom. Okay. So what does that look like? Well, when we show something going through beta decay, this is what we're seeing. So here's cesium again, and poor cesium is just going through so much. So now it's going through beta decay. Okay, so we draw our arrow. We show our beta particle here, plus. Now notice, we leave the mass number the same, and the mass number stays the same because there's no change in mass. We didn't lose anything, just something changed. A neutron changed to a proton. So our mass number stays the same. But what differs now is our atomic number is different, and because our atomic number is different, we have a completely new atom. And in this case, we went from cesium to barium. So how do we know it's barium, though? Well, we can just go here, look on our periodic table. So when we're told, well, cesium is going to go through beta decay, we're going to find cesium, and cesium is 55. So here's cesium. Here's cesium. Cesium is going to go through beta decay, and it's going to increase its atomic number. Okay, well, next one's 56. It looks like barium is 56. Boom, that's it. We got it, barium. Okay. And that's how we show and denote beta decay. Okay, so relatively easy, relatively speaking. Okay. All right, and then the last kind of decay that we're going to talk about before getting into a couple of just more or less just examples. Gamma radiation is also one. I mentioned this in the beginning, so we denote that with this weird looking Y. Okay, and this is a stream of high-energy non-particle electromagnetic radiation similar to X-rays. So think of it this way: gamma radiation is just energy, particles of energy, just and not exactly electrons, but just energy freely moving where it wants to go, through things, past things, and can be quite dangerous. Okay, and we denote it like this. So because it's energy, but it's just, we don't want to associate a charge to it. It gets zero, and it's zero, and then it has its Y signal here, symbol. Okay. And that's about as much as we talk about. So what you need to know about this is you need to know how we denote it, and you need to know what it is. Okay. Okay, and then there is a half-life. So half-life, now typically, most years we go through this, but because of COVID, we don't go through half-lives, just because there's just not enough time. This is the length of time required for half of a given sample of a radioactive substance to decay. That's about as much as I want you to know about it. It's more or less to say that if you have 10 grams of, if you've got 10 grams of carbon today, its half-life might be 10 years. So if you have 10 grams of that today, in 10 years you'll have 5 grams. Okay? pretty much that's what I need you to know about it. Okay, it's the length of time required for half of a given sample of radioactive substance to decay. Okay. And then there's nuclear fission. So nuclear fission is when a large nucleus is split into two smaller nuclei of approximately equal mass. So this is how atomic bombs make their devastation. It splits a nucleus into two, and this is how nuclear reactors power and generate energy by heating up water to then push steam through a turbine. Okay. And then you have nuclear, and I said fission. If I said fusion, I meant fission. So sorry if I may have cut. If I didn't, sorry for extra confusion. Nuclear fission. Here's nuclear fusion. This is when two smaller nuclei join to form one larger nucleus. So this is what hydrogen bombs do. And if you've ever heard someone reference that the sun is nothing but a giant, everlasting hydrogen bomb or collection of hydrogen bombs, that's why we call it that, because that's what the sun does. The sun, at every single given second, and for the next, 6 billion years, I think it is, the sun is going to be nothing but instantaneous, seemingly never-ending hydrogen bombs detonating at all given time. Okay, at any given moment, I should say. Okay, so again, two smaller nuclei join to form one larger nucleus.